Hi and welcome to part 5 of my video playlist about the best methods to oxidize primary alcohols to aldehydes. In this video we'll have a look at some reagents that are not usually used for alcohol oxidations, mainly because these are not as selective as the more common oxidants and often require a careful optimization of the reaction conditions. This would be the case for oxidations with chlorine, hypochlorite or nitric acid. Oxidations with manganese dioxide work well for allylic or benzylic alcohols, but an excess of oxidant is required and the huge amounts of waste make its use in large-scale preparations impossible. Chlorine is, besides oxygen, one of the cheapest oxidants available. Unfortunately, aldehydes are readily alpha-chlorinated by chlorine, and this side reaction is difficult to prevent. Here, for example, chlorination of hexanediol with chlorine in DMF mainly gave the hydrate of a tetrachlorodialdehyde. The preparation of chloral from ethanol is discussed in part 1 of this playlist. With bleach, however, alcohols can sometimes be oxidized to aldehydes without extensive chlorination, as shown here. An excess of bleach should be avoided, though. This is another example of the oxidation of an alcohol with bleach. As on the previous slide, bromide was added as co-catalyst. Also in oxidations with aminoxyl radicals, bromide greatly enhances the reaction rate and can increase the selectivity of the reaction. Here the alcohol also contained two CC double bonds, which were however not chlorinated. N-haloimides can sometimes also be used to oxidize primary alcohols to aldehydes. In this example, isulfenamide was used as catalyst, and the oxidation was assumed to proceed by a mechanism similar to the Swern oxidation. Catalysis is, however, not strictly required, as shown here. In this example, a hydroxymethylpyridine was oxidized to an aldehyde by an excess of NBS and carbonate. Nitric acid is a powerful but unselective oxidant. Upon heating, concentrated nitric acid will react with almost any organic compound. On the other hand, it is also an environmentally friendly, inexpensive reagent, which produces little waste and is prepared from air and water. Thus, for large-scale oxidations, it is definitely a reagent that should be considered. In this example, a hydroxymethylimidazole was oxidized in fair yield to an aldehyde by heating with concentrated nitric acid. A better yield could be attained in this example, where a similar oxidation was conducted in dichloromethane at room temperature. In this example, the nitration of a substituted benzyl alcohol yielded a dinitrobenzaldehyde. Interestingly, despite the strongly acidic reaction conditions, no cleavage of the terz-butyl group from the arene occurred. Manganese dioxide is well suited for the selective oxidation of benzylic or allylic alcohols. Simple aliphatic alcohols, though, usually react much slower and can be difficult to convert into aldehydes with this oxidant. In this example, a propargyl alcohol was selectively oxidized with a large excess of manganese dioxide in the presence of an aniline and a primary aliphatic alcohol. Here an allylic alcohol was oxidized selectively. Despite the huge excess of manganese dioxide, no oxidation of the secondary hydroxy group or the methoxybenzyl ether occurred. Similarly, in this example only the benzylic hydroxy group reacted, while the primary alcohol remained unchanged. Thioethers are compatible with manganese dioxide and will not usually be oxidized by this reagent. This is not the case, however, with chlorine, hypochlorite or nitric acid. Many things can of course go wrong with these unselective oxidants. For a more detailed discussion of side reactions, you may check the first 4 videos of this playlist. Aromatic and heteroaromatic aldehydes are chemically much less reactive than aliphatic enolizable aldehydes, and therefore easier to prepare. Benzyl alcohol can, for instance, be cleanly oxidized to benzaldehyde by treatment with calcium hypochlorite. Under identical conditions, primary aliphatic alcohols are converted, however, into the products of the Tichenko reaction. Here are some more references which I've also listed in the description of this video. I've also included examples of oxidations with chromium reagents, but these are only rarely used today. Oxidations with hypochlorite and TEMPO or with IBX are more convenient and do not generate transition metal waste. Here are some additional reagents. Oxidations with catalytic perruthenate were popular in the 90s, but do not seem to offer significant advantages if compared to the other reagents I've presented so far. Oppenauer oxidations only rarely allow the preparation of aldehydes, and the products can be difficult to purify. Quinones have occasionally been used with success, but again, the resulting hydroquinones can be difficult to separate from the product. Some alcohols can be oxidized with stoichiometric amounts of copper sulfate or with titanium tetrachloride and triethylamine, but the large amounts of waste make these methods inferior to other strategies. To summarize, for small-scale laboratory oxidations, the most practical reagents are DMSO, IBX, and bleach combined with TEMPO or tetramethylpiperidine. For the large-scale preparation of expensive aldehydes, bleach combined with TEMPO and bromide or borax as co-catalysts, as described in part 2 of this playlist, will probably be the best choice. And if huge amounts of an aldehyde are to be prepared from an alcohol, oxidations with air, chlorine, hydrogen peroxide or nitric acid should be considered.